Okay, so in this movie clip, let's get into some more details how to do and complete the electrostatic analysis. So let's see. Okay, so the game plan is as follows. First, we should look for the built-in potential VBI across PN junction diode. Afterwards, we're gonna use the depletion approximation as we have learned. This depletion approximation is a core part when doing PN junction diode. When it comes to the PN junction diode theory. So again, the depletion layer has been well limited and set across PN diode. Mathematically, we have used the minus XP and plus XN. So in between minus XP and XN, all the free carriers such as electrons and holes are removed. They are diffused away into the other side. So only the ionized dopant atoms are left behind. So that is the main physical origin. How come the charge density is non-zero near the interface between p side and n side? So once we found the charge density plot, you remember this, okay? Then uh, the job left behind us is it's a kind of a mathematical problem set, right? So just to solve integration problem to look for the electric field intensity EX across X direction. So we should have two boundary conditions. So at the boundary of the depletion layer, the electric field intensity is zero. So using those two boundary conditions, we can easily and simply complete the integration job. Afterwards, we need to do another integration work to look for and to obtain the potential across the PN junction diode. So, as done in this integration work, we need another two boundary conditions. That is, potential value at minus XP is zero. So we have defined that this is the reference voltage at X of minus XP. Afterwards, at axle xn, the opposite side of the depletion layer has been defined and it has its own built-in potential. So we have no idea what this value is, but symbolically and logically we have used the V sub bi. Okay. Afterwards, we are gonna do one more step in this lecture note. We're gonna look for the some a one more condition to meet the physics. The electric field intensity should be always continuous across p-n junction diode. So in that sense, at x of zero, at the physical contact between p and n side, the electric field intensity should be continuous. So using this condition, we may derive one more equation. Afterwards, in the end, we're gonna solve for xp and xn. That means we can estimate quantitatively the depletion layer width of PN junction. Okay, so for given PN junction diode, so the depletion layer should be formed in between. Then now we can claim that say 100 nanometer depletion layer has been formed. So why is it important? Going back to the MOSFET, since you have some chance to look for the cross-sectional view of the MOSFET, say this is a p-type substrate, n plus source and n plus drain, and that is another PN diode, right? So you may heard that there are some huge depletion layer are formed below source drain as well as gate oxide layer, and later on this, you know, depletion layer would play a role of capacitance component in MOSFET. So if you take a look at the you know symbol for MOSFET, some textbook is drawing like that, some parasitic capacitance. Even here, the parasitic capacitance are there. So this parasitic capacitance comes from this depletion layer, the low oxidation layer. Then you should have the value for this parasitic capacitance. How much is it? Well, depending on the depletion layer width. So now we are almost ready to get the depletion layer below oxidation layer as well as a source and drain region. So this parasitic source to say this is body. So C, SB, C drain body, those stuff will be estimated quantitatively. So in that sense, p-n junction theory is the most basic building block in understanding the parasitic capacitive components in MOSFET in integrated circuit. So I guess that this class would provide you with some more basic and fundamentals of how to, why, or the physical origin of capacitive components in MOSFET. How come the capacitive components are always hanging together with resistance components? Yeah, that must be originated from the depletion region. So how come the depletion region would be formed between p side and n side? The answer would be found as well in this lecture note. Take a look at this slide. Built-in potential V sub Bi. What is this? Yeah, in the last movie clip, I have commented that we have two different dishes, P dishes and N dishes, and the amount of water is corresponding to the number of electrons. So N-type material has a abundant number of electrons, so it has contained tons of water. But P-side P-type dish has a very small amount of water. Okay, then imagine that two dishes are combined together and it will become a PN dish. Then it would have its own water. Well, some part of water will be shared into the P-type dishes. Okay. And then what kind of physical or physics or you know natural forces would uh, be engaged in this PN junction? Yes, this built-in potential. So let's take, I guess, with your knowledge, I guess let's draw the NH band diagram. And that would be much easiest way to catch how the PN junctions are formed and how come the built-in potential has been set up. So P side and N side, this is Fermi energy level, that is Fermi energy level for N side. So if I combine them at this point, so just you can elongate the band edge line and Fermi energy level as well. Then afterwards, there is a potential difference. I mean you know, here the water surface looks different, but once they are combined together, no water difference. That means the Fermi energy level in N side is single valued. The Fermi energy level in P side is single valued. However, once they are combined and once they become a PN diode, then this EFP and this EFN should be aligned together because they are single system. Then what kind of things would be happened behind? Yes, band bending. So why band bending would be happened? Yeah, there are many holes. They are moved and diffused into the N side. There are many electrons. They would prefer to be diffused into the P side. So in the end, here no electrons, here no holes. So depletion layer would be formed on both sides. While those free carriers are diffused into the other side, the depletion layer is simultaneously formed, then the Fermi energy level would be moved downward. It looks like, most of the waters are spilled over into the P side, so the water surface has been moved downward. So same thing can be happened in N side. So once electrons are moved into the P side, the Fermi energy level would move downward. and on opposite side, the Fermi energy level for hole would move upward. So in the end, they're gonna meet together. So in this process, the band diagram would become like that. So EFP is equal to EFN, and the band diagram. In the band diagram, you can see that the band bending has happened and internally formed, I mean the built-in electric field would be happened. Okay, so where does this electric field, built-in electric field comes from? Yes, donors and acceptors. They're gonna make a plus charge the region and minus charge the region. So that is the main origin of this built-in electric field. And then how much built-in potential would be happened? Where does it come from? Yes, this. Originally, there is Fermi energy level difference. So this Fermi energy level difference would induce the band bending. So this band bending is the energy difference is well matched to the originally how much Fermi energy levels are uh, away from each other. Okay, so this EF p side and EF n side, this energy difference is corresponding to the built-in potential, but since to match the unit, I'm going to use this. Okay, so on the very first line here, the built-in potential times unit charge in terms of electron volt, the energy is equal to what? Yes, here. If I cancel out E sub I, then EF n side, EF p side minus. So EF n minus EF p. Okay, so on the right hand side, you can see that the Fermi energy level difference coming from the original p side and original n side. Take a look at this here. The energy difference that is corresponding to the how much water surface has been away from each other. So take a look at here. So right before P and N are combined together, how much water surface difference has been formed would give us the idea how much built-in potential would be formed. Okay, so Q times VBI is physically originated from EFN side minus EFP side. Okay, however, here just for your information, I have used the intrinsic Fermi as level. So here, this and that. So those are one here and two here. So 1 plus 2 are equal to the built-in potential energy. So using the equation that we have learned, the kind of 60 millivolts load that I have explained in class. Once you know the doping concentration here, then you're gonna know the majority carrier concentration. And using this equation, you can estimate uh, the position of Fermi energy level in the band diagram with respect to the mid gap or intrinsic Fermi energy level here. So say P side, acceptor concentration is 10 to the 15, then here EI minus EF, this energy difference comes from 5 times 0.06 electron volts, so zero point 0.3 electron volt. Okay, so the band gap energy is 1.12 electron volt, and but this EI minus EF is zero point 0.3 electron volt. So you can do this practice by yourself, and since we have already done this practice a lot, so now you can quantitatively as well as qualitatively uh, analyze the PN junction diodes and a span diagram. Okay, so here in the key concept is built-in potential can be estimated from EI minus EF plus EF minus EI, or how much Fermi energy level difference has been set up right before P-type is making a contact with two N-side N-type silicon material. So this built-in potential concept can be easily and intuitively understood with two different dishes. One dish has a less amount of water, and the other dish with more water. Then the water surface height difference would give us the idea built-in potential. Okay, so I guess one more thing that I want to uh, teach you is here. Built-in potential for one-sided p-n junction. So why one-sided p-n junction is significant and why we should understand it is, as I have told you, that in MOS device, the source drain side is heavily doped, but body side is lightly doped. So here, Pn plus. One side is very heavily doped and the other side is lightly doped. So this Pn plus, one-sided p-n junction has been widely found in a real device in integrated circuit chip. So in that sense, let's repeat and do the analysis for Q times 3BI for one-sided PN junction. But there is no something special because if one side of PN diode is heavily doped, uh, one of the values, say this is p, in case of p plus n, p side is very heavily doped and EF is very close to the EV. So EI minus EB is equal to half band gap. Okay, so say that 10 to the 20 p plus side, and here n side 10 to the 15. That in this case, the built-in potential, how much is it? You can simply do that. This is degenerately doped p-type material, so the built-in potential, the contribution for built-in potential from p side is half band gap plus here 10 to the 15, then 5 times point, 0.06 electron volt. So the answer is this is 0.06, 0.3. So if we combine them, some 0.86 electron volt. Okay, that's it. What about the n plus p? Yeah, same. If since the n side is heavily doped, so here EF is very close to the conduction band edges, so EC minus EI is almost equal to the half band gap. So the key thing in determining the built-in potential of n plus p comes from the how much acceptors are included in the lightly doped side. Okay, so in summary, in one-sided p-n junction, the likelihood of the side has its own key in determining the built-in potential. The heavily doped side is doing almost nothing when it comes to determining the built-in potential. Okay, so the lightly doped side is more significant and important. And the in this slide, I guess you can see that the depletion approximation again. So as we have done in MS diode, so let's reuse the depletion approximation. So here at x of minus xp and here at x of xn, the charge density in this neutral region is 0, and here in this neutral, the pure n-side region, the charge density is 0. However, in the depletion region, the charge density is not 0 anymore. So in the next movie clip, I'm going to tell you some more details how to use a depletion approximation for PN diode. So okay, that's it. See you in the next movie clip. Bye bye.